Welcome everyone. I'm going to present my paper titled Local Differentially Private Matrix Factorization with MoG for recommendation in the 34th Annual Conference on Data and Application Security and Privacy. So in this presentation, initially we are going to look at what is local differential privacy and why it should be used, and then I will explain about the problem that we are addressing in my paper. After that, I will go through the details of the proposed system design, which will include both the input perturbation mechanism and the Gaussian mixture prediction model. Later on, we will look at how our proposed system performs accuracy-wise against the existing methods in the literature. I will guide you through the experiments we carried out, and also we will see the results that I have got. So as you know, recommendation systems are widely used by service providers to recommend items to the users which might be of their interest. Today's technology has made it possible for service providers to aggregate a lot of personal data, and through their platforms they are able to aggregate and analyze information related to users so that they can recommend items in return. However, these aggregation and analytical practices of service providers, even though they enhance the experience of users, they can cause privacy violations. For example, in 2001, researchers from University of Texas, they were able to de-anonymize Netflix data and also was able to infer the personal preference of some users. Such data leakage raises so many questions, and one important question that it raises is how we can ensure the privacy of users are protected, especially in recommendation systems. So throughout the time, there are several privacy protection models that have been proposed in literature. The one we are interested in is called local differential privacy, which is a variant of differential privacy model. If you are aware of differential privacy protection model, it's a very strong privacy protection model. Normally, differential privacy protection model is used in the settings of centralized differential privacy. So in centralized settings, what happens is we have three parties: the user, data aggregator, and the data analyst. So the user sends their original data to the data aggregator, who aggregates all the user's original data. And the data analyst, whenever they want to perform some analytical task, they send a query to the data aggregator, who will perturb the answer of the query, so they won't be giving the real answer, and sends the perturb answer to data analyst. So in these settings, the data aggregator is called a trusted entity and the data analyst is called an untrustworthy entity. However, the problem here is sometimes data aggregators can cause accidental or purposeful data leakage. If you take Cambridge Analytica, the case of Cambridge Analytica, you can see the data aggregator also is liable for the data leakage that was caused. So even though they were considered trusted, at the end of the day, the data leakage was caused by a trusted data aggregator. So this is where the local differential privacy based privacy protection models comes into play. So in a local differential privacy based privacy protection model, the original data from user is perturbed using a mechanism, and the perturbed data is sent to data aggregator. So in this model, the data aggregator does not get to see the perturbed data. So does not get to see the original data. So the definition of local differential privacy is given here. So a mechanism Q will provide epsilon local differential privacy if for any input x and x dash, which is in the set of all input, and for any output y, which is in the set of all output y, if this particular condition holds. What this literally means is that the adversary, who might or might not have background knowledge about the user, will not be able to infer the original data from the perturbed data. So just by observing the perturbed data, they are not going to infer anything about the user. The epsilon here is called the privacy budget, and when the epsilon is small, the privacy of the user is strongly protected. There are so many mechanisms that are used to perturb the user data. For example, Laplace mechanism can be used, randomized response mechanism can be used, and also there are specially designed mechanisms like RAPO which can be used. So using local differential privacy gives you three advantages. One is this local differential privacy protect the privacy of the user even against adversaries who has background knowledge. So from data aggregators or even a third party adversary, it gives strong privacy protection for users. The original data will not be known by the data aggregator, which is not the case in a centralized differential privacy setting. And at the end, the privacy of users are protected not only from third-party adversaries but also from trusted and untrusted data aggregators. But there's a problem in local differential privacy. So as I said, local differential privacy is used widely in different applications. So Google uses local differential privacy to estimate relative frequency of their Chrome home page. And the Microsoft uses local differential privacy to estimate the histogram of their daily app usage. So many people use local differential privacies in their applications. However, local differential privacy has a main problem, which is the utility issue. So if you take the local differential privacy setting, so say there are n number of users and then you get n number of original data, and each and every original data is perturbed using an LDP mechanism, and the noisy data is aggregated at the data aggregator's end. So what data aggregator has is the noisy data. So if you take recommendation system, the data aggregator has to perform recommendation over the noisy data, which is not actually the original data. So when they perform recommendation over noisy data, the users at the end who gets the recommended items might not get more accurate results. So their user experience is going to get affected. So that is the main problem in LDP. So when you add noise individually to user data, it's going to cause a lot of perturbation, which at the end will result on loss of utility at data aggregator. So what we are trying to do is, in our paper, we are trying to propose a system which will protect the privacy of the users. At the same time, it will also give some utility to data aggregator. So this is a system, this is the overall system design. So as you can see, we are looking at only aggregation of ratings. So in the local side, that is at the user side, the user will enter the true rating, which will go through the LDP perturbation mechanism. So in our case, we are using a perturbation mechanism called Bounded Laplace mechanism. And using this mechanism, the perturbed ratings are created, and created perturbed ratings are sent to the data aggregator. So we are considering an untrustworthy data aggregator here. So the users are not willing to share any sensitive information with them. So at data aggregator side, we do the rating prediction. So for that, we use a matrix factorization method with Gaussian mixture model. So it does what it does is it estimates the noise that is added to the original rating, and also at the same time it does the rating prediction also. So at the end of the day, this particular rating prediction model will give recommendations to the users. So first we will go through the perturbation mechanism, which is the bounded Laplace mechanism. So bounded Laplace mechanism is bit different from the Laplace mechanism. because bounded Laplace mechanism, it sanitizes the output results. So it has a bounding constraint, so it does not perturb the rating in the first instant. Instead, it resamples noise until the output rating falls within a predefined domain. So this algorithm gives you an idea of what is a bounded Laplace mechanism. The detailed explanation and definition of bounded Laplace mechanism is given in the paper. So I'll go through the algorithm first. So the input for bounded Laplace mechanism will be the original rating, and the output of the bounded Laplace mechanism will be the perturb rating. So when the user enters the original rating, the bounded Laplace mechanism will first generate a noise sample from the Laplace distribution which has mu 0 and variance b. So then it will calculate the perturb rating, so which will be adding the generated noise to the original rating. We will have a domain, a bounding constraint, and the perturb rating will be compared against this bounding constraint, whether it falls within this particular bounding constraint. If this perturb rating falls within the given constraint, then the perturb rating is set to R star. If not, then we will regenerate the noise sample until this perturb rating falls within the given bounding constraint. Once the perturb rating falls within the bounding constraint, we will then send the perturb rating to dA. So the advantage here is, unlike Laplace mechanism, which has a domain from minus infinity to plus infinity, here we have a bounding constraint domain for the perturb rating. So we are not having meaningless ratings. We will have ratings which make sense or which has actual value, actual meaningful values. But we are not violating differential privacy principle here, which is also I have given the proof in the paper, because one is, to summarize what I have said in the paper, we are not limiting the range of the noise. Instead, we are regenerating the noise and recalculating the perturb rating until it falls within the given range. The next part is the noise estimation, which will be done with Gaussian mixture model. I'm going to guide you through how the noise estimation and the rating prediction will be done. However, the detailed explanation of each and every equation and how they were derived are given in the paper. So R is the original rating matrix, R star is the perturb rating matrix, and E can be considered the noise matrix. So you can represent R star using R plus E. So in that case, we can also represent each element in the noise rating matrix R star given in this equation, where it can be, each element can be represented saying Rij plus Eij. As you know, in matrix factorization, the original matrix can be represented using two latent factor matrices. One is the user latent factor matrices and the other one is the item latent factor matrices. So this equation can be rewritten as Ui transpose into Vj plus Eij. As you know, any unknown distribution can be modeled using a mixture of Gaussian. So we assume that the noise which is drawn from bounded Laplace mechanism can be drawn from a mixture of Gaussian distribution also. So the probability the noise is drawn from a mixture of Gaussian can be indicated using this equation. So here sigma k is the variance of the Gaussian component k, and pi k is called the mixing proportion, which indicates that how much a particular Gaussian component plays a vital role in generating this noise distribution. So the probability of the perturb rating R star from the previous equation can be given as this given by, can be represented by this equation. So our goal is to compute the parameters u, v, pi and sigma so that the maximum likelihood of R star is achieved. So this is our optimization problem. So the problem here is the optimization problem we have here is cannot be solved using a closed form solution. Therefore, we use expectation maximization method to solve our optimization problem. So in expectation maximization, you have two steps. First is the E step and the second is the M step. So in E step, we compute the posterior responsibility of our current model of posterior responsibilities of each data point, noise point, using the current model parameters u, v, pi and sigma. In M step, we re-estimate the model parameters u, v, pi and sigma using the equations that are also given in the paper. We also update u and v. When you look at the how we have derived in the paper how updating u and v becomes a weighted L2 low rank matrix factorization problem. So we are going to use any weighted L2 norm solvers to solve this problem and derive u and v. This is the MoG algorithm that we came up with. I have explained how this algorithm works in the previous slides. In this algorithm, as you can see, the convergence is achieved when the change between two consecutive user latent matrices is smaller than a predefined threshold, or if the maximum number of iterations is reached. So that's one thing that you have to keep in mind. Okay, so the next part of my presentation is about the evaluation. So in order to evaluate our model, I compared my results with another three models. First model is called a non-private matrix factorization. So non-private matrix factorization is the baseline method we are going to compare our approach with. So in this method, we are not perturbing any user ratings, and we are using SVD based matrix factorization for rating prediction at DA. The RMSE values of the baseline method reflects the lower bound for prediction error that can be obtained without any privacy constraints. The second method I'm going to use to compare my results is called input perturbation SGD method. In SGD method, they used a calibrated Laplace mechanism to perturb each user's ratings. The key idea here is to perturb the rating using Laplace mechanism and clamp the resulting perturb rating using a clamping parameter if it goes out of bound. So this is done locally at the user device. And at DA, again we are going to use SVD and in order to you do the rating prediction. The third method I'm using is called private gradient matrix factorization. This is a bit of a different method than what we looked at before. It's different than the method that I proposed, but we compared our method against this because this was one of the recent method that was introduced in a research paper. So in here, what happens is initially item latent factors are computed at DA and are sent to each user. Then each user will compute their latent factors locally in their device and submits a perturb gradient to DA. Aggregated perturb gradients from each user will be gathered by DA, and the DA will update the item latent factors, and at the end of the day they will do the recommendations and send it back to the users. So here what they did is they used a randomized response mechanism in order to perturb each user's gradient. So we use two data sets in order to compare our method against the other methods. So we use Movielens, which is a 100K ratings rating matrix, and we use Jester, which contains 2 million ratings. And we use RMSE, root mean squared error metric, to evaluate the accuracy of our method against other methods. So the first results, this diagram, I just wanted to point out here how bounded Laplace mechanism differs from the traditional Laplace mechanism. As you can see, the noise drawn from Laplace mechanisms approximates to a Laplace distribution, whereas the noise generated from bounded Laplace mechanism does not approximate to a Laplace mechanism. Instead, it kind of can be represented as a continuous distribution, which also can be represented using a mixture of Gaussian. So the next result is the prediction accuracy. So we are going to look at how our prediction accuracy fares over other methods that we compared against. So first, we compared our method against the PGMF method. We varied the privacy budget from 0.1 to 1.6 for Movielens dataset. And as you can see, the RMSE values for both methods starts to decrease with increase of privacy budget. Because increase of privacy budget implies that the magnitude of privacy leakage the mechanism allows is substantial, which in return leads to an increase in the utility, which is what we call the prediction accuracy. However, you can also see the PGMF method performs fairly worse when compared to our method, which gives higher prediction accuracy, especially when epsilon is less than 1. The next results shows how our method performed against the ISGD method. So in this experiment, we changed the privacy budget from 0 to 3 for both Movielens and Jester datasets. As you can see, the ISGD method did not perform well compared to our method, and our proposed method continued to give higher prediction accuracy for higher values of epsilon and also for lower values of epsilon. Another important thing that you can note here is the difference of the RMSE values for Jester and Movielens dataset. Now, Jester is a sparse dataset, so there's not enough data in that. However, you can see our method gives higher accuracy increase compared to Movielens dataset in Jester dataset, which implies that our method can outperform the ISGD method even when the data is sparse. So as a conclusion, so in our method, in our system, the proposed system, we use bounded Laplace mechanism and mixture of Gaussian. In average, there were at least 10% accuracy improvement across all privacy budget compared to other methods. And especially when for smaller privacy budget, we also saw at least 20% accuracy improvement compared to other methods. Apart from that, our method incurs very less communication cost compared to PGMF method because we do not send back and forth the user latent matrix. So only the users, they perturb their ratings, they send to the data aggregators, and that's it. They don't have to do anything else. In future, we also wanted to look at how we can provide individual privacy budget for each user rather than the global privacy budget. Thank you, and thank you for listening for my presentation.